Hi, everybody. Glad you can join us. Welcome to the deep dive of VM to host Affinity. As you can see, we are using the YouTube live event. You have a chat window on your right. We will take questions at the end of this presentation as time allows us. Comments and questions are also welcome under this video page or in the oVirt users mailing list. Basically, we will talk about VM to host Affinity feature. We will give an overview on Affinity in general, since it closes VM to host Affinity. So we'll get a quick overview and then deep dive inside the VM to host Affinity feature itself. Okay, so let's get started. Okay, so our agenda, we will discuss what is Affinity, use cases where Affinity might come into hand, and an overview. VM to host Affinity in more details in terms of scheduling, REST API and SDK, Affinity Rule Enforcer Manager, and possible conflicts that may arise from these Affinity groups. We'll get into that later on. Okay, so basically, what is Affinity? Affinity is a relation factor between virtual machines or virtual machines and hosts. Basically, we define the relation between these virtual machines or virtual machines and hosts by creating these type of groups or labels, which we won't cover in deep matter here. But these options all exist for Affinity. Basically, relations can be strong and soft. We'll discuss it in the next slide. And positive, negative, meaning together or apart. Okay, so basically, these affinities will be automatically enforced by our process. We have an ongoing process, which we'll discuss later on. They will be automatically, these rules will be automatically enforced for virtual machine placement. Basically, we want to talk about Affinity. It's worth mentioning the point that Affinity is less strict than pinning. If we talk about pinning means that a VM is confined to a hosts, and migration is disabled. With Affinity, the VM can migrate between a group of hosts in any situation. For example, we can define a relation between virtual machines, A and B for that example, to reside together or apart. But we don't care about how the relation will be satisfied, in contrast with pinning. For most Affinity relations, or all of them, the VM can be started, migrated if they are not satisfied. We'll talk about it with soft Affinity and VM to VM Affinity. VMs can dynamically adapt to the current cluster situation and load using Affinity. Okay, so again, we talked about Affinity in general. So we need to describe the type of affinities we have. So as you can see on the right, we have the hearts that we will use later on in this presentation to demonstrate the types of affinity. So we're talking about strong or soft affinity. Strong affinity means we cannot allow any violations. Strong affinities will be described here in hearts colored in red for a strong positive affinity, and in blue, a broken heart for a strong negative affinity. Soft or weak affinity are described in the grayed out hearts. This means that soft affinity is a best effort. We might still allow violation of the group, meaning if I have an affinity defined for a VM to a VM or a group of VMs with VMs that should run together positive affinity, or not together, negative affinity. If it's a soft relation, it's a best effort. We might still allow it to VM to run with a VM or not to run with a VM, although we have an affinity group defined for it. Same goes to VM and hosts. We will also talk about scheduling policy factors with soft affinity later on, and we'll demonstrate that as well. Okay, so affinity management in oVirt, as I said, we have two major types of affinity in our system. Affinity labels. Affinity labels are quite simple. You can look at them basically as requirements for a VM that wants some requirements from a host. Some example for requirements: we want a VM to run such on the host that satisfies DB requirements, finance requirements, some services, weak or strong requirements. A VM can only be scheduled on a host that is labeled with all the affinity labels that a VM has, same as the examples I mentioned earlier on. If a host has extra labels, it makes no difference. So in that manner, users will be able to create a logical subcluster of VMs and hosts using the desired labels they want. This type of affinity for affinity labels is only strong positive, as you can see in the red heart. Other type of affinity is affinity groups, which will be our main focus here, especially VM to host. In terms of types, VM's affinity groups are more advanced. As I mentioned earlier on, all the types of affinities, strong or soft affinity, positive and negative, they can all have these types in contrast to affinity labels. So again, the relations can be strong and soft, meaning must or best effort, or positive, run together, or negative, run apart. Again, a VM cannot reside with other VMs or need to reside with other VMs. And again, same goes to VM with hosts. Defining these type of affinity groups or affinity labels together might cause some conflicts, logical conflicts that the user might create. I'll show some examples later on. Most of the conflicts are in the responsibility of the user to avoid. We will warn about them. Some of them will be denied by the system. Okay, so again, just a quick recap about the affinity groups. We can define a group of VMs and the relationship with each other. And we can define a group of VM and hosts and the relationship to each other. One point that we'll mention again later on is no relationship. It means we can define that we have a pure VM to host group, because in an affinity group in our UI and REST, we can define also VMs and also hosts, and we want a way to show that this group only represents VM to host and no VM to VM affinity. Okay, so let's get a bit into the reasons or use cases why we need affinity at all. So we have here a bunch of use cases. I'll go briefly on each use case, maybe show how affinity comes into hand. So according to these points. So in terms of licensing reason, we want to keep the number of nodes with existing licenses and minimize cost of purchasing additional licenses, as you well know from real-life situations. And we have VMs that run that software, and we want to bound them to the required nodes. We don't want them to run on other nodes or other hosts, and want to define a way to keep them on these certain hosts for these certain VMs. So if I have several VMs that require to run software with a license, we can bind them with affinity to these nodes, let's say VM to host affinity for that matter, without letting them scatter around on hosts that doesn't have this certain license. Other uses can come into hand here, but this is one example of it. Okay, in terms of high availability, Affinity, for that matter, negative affinity, provides a way to separate VMs that provide failover to each other. Meaning, if a VM falls, a backup VM takes his work instead. So if we provide a failover to each other for VMs by keeping them on separate hosts, we ensure that we keep high availability. That if a host will hold one VM and another host will hold the other, so one crash of a host won't affect the other VM, and we'll still keep high availability. So creating a negative affinity group with these two or more VMs will provide us the tool to keep them separate and to keep high availability. Security reasons. So think about a case where we have VMs with sensitive data. Let's say they are handling credit card numbers or some secure data that we need to handle. But this is one example. In some real-life situations, these VMs can be accessed from other VMs. And by this availability or access, we can compromise the sensitive VM's data. One example for this kind of attack, it's called cache-based timing attack. So here, with negative affinity between sensitive VMs and other VMs, we can prevent such attacks. We're placing sensitive VMs with good neighbors, meaning we'll put only sensitive VMs together, or with strong positive affinity, or keep sensitive VMs with not so sensitive VMs or not so secure VMs apart from the sensitive VMs with negative affinity. In terms of performance aspects, we want to keep VMs according to their functionality close to the best fitting resources. We can use here VM to host soft or strong affinity, affinity to hosts that are close to the gateway, for example, for low latency, or affinity to a data center for faster reads from the DB, for example. Again, in terms of performance aspects, client locality, we have an example later on with failover. In terms of host hardware consideration or constraints. So we can use a soft positive affinity here for a host hardware consideration. By using soft positive affinity, we can keep high availability as long as the host is up. For example, VMs that have soft positive affinity will try to run on a host that is more desirable for them in terms of faster CPUs or better NICs, storage cards, etc. But in case these hosts are down, the VM is not confined to these hosts. The affinity is soft, so the VM will migrate to another VM as a failover. And once the host is back up, because we have an affinity, a positive affinity between the VM and that or these hosts, the VM will migrate back. This way we keep high availability and most of the time keep the VM close to its preferred resources. Dynamic subclusters. If we want to change the cluster according to our needs dynamically, we can use affinity labels that I mentioned earlier on, with labels such as DB, web servers. This way we can separate the cluster into logical units. We can extend or shrink these logical units as needed, meaning I want a certain amount of hosts to run our servers or DB or web services. So we can extend or shrink these services needed. As well, we can let other VMs with no labels run anywhere on the system. With this with this option, we can also allow zero downtime, and the cluster will adapt in time with our definitions. In terms of maintenance, operation, and planning, let's say we want to put a host or hosts in maintenance, and we want to migrate these VMs that are running on these hosts in a gradual manner. So migration of these VMs off a host, at least for a major percent of them, we can use a negative affinity, meaning we will define a negative affinity group. And with time, these VMs will migrate off the target host, or the source host. So in that manner, that when we want to put the host in maintenance, it will have no VMs or minimum amount of VMs, and it will be more easy to put the host into maintenance. Soft affinity to host for the rack case use case. In case of failure, it won't be enforced. Again, we're talking about keeping certain services close together, meaning affinity of certain VMs with their services they provide with a designated host. As I said earlier on, soft affinity will ensure that if we fail, we won't be on that host, but once it's back up, the VM will migrate back to that host. Okay, so here's a good example for soft affinity. Let's say we have a VM that runs close on its server that is close to it in terms of connectivity. This host fails, so the VM migrates to another VM that is far away in the network. So it means the performance is hindered. But once the host is back up again, the mechanism will migrate the VM back because of its VM to host affinity. So we have live migration here, no downtime, and get our VM back close on its host it needed. Again, I'm talking here about a simple use case of VM to host. Other considerations are need to take into account here in terms of scheduling and other factors. So affinity group in the user interface. Currently, in our system, we have only via the user interface a way to define VM to VM affinity. But in order to keep backward compatibility, we changed the VM affinity rule. Now we have a free state VM affinity rule, positive and negative as it used to be before. But we added the disabled option. Disabled option means that the affinity group is pure VM to host, meaning that if we have a list of VMs, the affinity between VM and a VM won't be enforced, only VM and hosts. VM and hosts we will define via REST API and SDK. We'll show that later on. Okay. So to understand how strong and soft affinity are used, we need to understand the scheduler. So let's give a quick overview on the scheduler logic in the slide here. Well, so the scheduler uses a process that gets a VM scheduling request. It applies hard constraints and soft constraints to get the optimal host for that request and at that point of time. We can observe two aspects of the scheduler in the diagram. On the left, we have the filter, a basic logic unit which filters out hypervisors who do not satisfy the hard constraints for placing a given VM. These filters can be used by known filters for memory, CPU, of course, affinity as we discussed, and I'll show later on. Same goes also for the cost function, meaning weights on the right. The cost function is a function that gives a score to a given host based on its internal logic. This is a way to implement soft constraints in the scheduling process. So the scheduling process will take all the relevant hosts and run them through the relevant filters at the first stage. You can note that from one filter to another, the host numbers may decrease. The filter host list will then be used as an input to the relevant cost functions, which will create a cost table on the right. From that, the best host or the best candidate host will be selected, and the VM will be migrated or try to be migrated to that host. VM to VM and VM to host affinity filter units are included here, of course, and filter out the host accordingly. And so if we look at the cost table indicates the host with the lowest cost, which is the optimal solution for the given request. So VM to VM and VM to host affinity weight units are included here and grant a score to a host by the number of violations. Each violation increases the weight by 1, and then they are multiplied by the factor. Violation of a host is an unsatisfied rule of an affinity group. Let's see an example here. So basically, let's see how we count number of violations of a host. So imagine the following scenario. We have 3 hosts in a cluster, A, B, and C, and we have VMA that is up for scheduling. In our system, we have 2 affinity groups applied for the cluster. We can see VMA with negative strong affinity to host A, and VMA with soft positive affinity to hosts B and C. So VMA, by having a negative affinity to host A, causes a violation for host A because we want to run VMA, but host A cannot supply VMA to run on it. So the number of violation is up by 1. Moving on to the other affinity group, VAA can run on host B and host C, and VMA is not mentioned here. So host A that is not mentioned in this affinity group is considered as a violation, and the violation count rises by 1 as well. So we have total violation counts of 2. This is the score. The score is then multiplied by the factor, and is taken into account in the score function. So again, we said a VM will be scheduled according to the rules defined in affinity groups, a part of it, as we said in the score functions. VM affinity filter and weight policies units are now modified to exclude affinity groups when the VM affinity rule is disabled, as we said. If the affinity group is only pure VM to host, so these type of affinity groups won't apply on VM to VM affinity filter. Now we have 2 new filters here, 2 new policy units, VM to host affinity filter policy unit, and the VM to host affinity weight policy unit. Regarding the weight policy unit, I showed how we count violation and then the score, and VM to host affinity filter, which physically applies filtering of hosts, meaning it's applied only for strong affinity. VM to host affinity weight is applied for soft affinity. Okay, so we can see in the user interface we have the two policy units, VM to host affinity groups under the filters and VM to host affinity groups under the weights. As you can see, we have a factor unit here where we can increase it or decrease it according to our needs, meaning that if we had other factors here and we want to put emphasis on VM to host affinity, we need to increase the factor. We'll discuss it later on in Affinity Rule Enforcer, see what is the importance of changing the factor here in order to enforce our desired behavior. Okay. So I mentioned earlier on the Affinity Rule Enforcer or the Affinity Rule Enforcer Manager. The Affinity Rule Enforcer runs in the background. It's a separate process. It checks for violations of affinity groups I mentioned earlier on. VM to VM affinity, VM to host affinity, strong and soft. Worth mentioning that VM to VM affinity is only strong affinity here that is being checked. We choose a violating VM, then choose a candidate host and migrate if possible. By introducing the VM to host affinity and affinity labels, as I said, we can have possible conflicts, and we will warn about them in this process logs that you can see in engine log. And we have one migration of a VM at a time, meaning we have an interval here, and each interval we migrate only one VM if possible. So let's see the process itself. We need to see that each of this process is per cluster. Per cluster, this process is happening. So from the beginning, we defined an interval for the rule enforcer, and the default value of the interval is 1 minute. We check, again, per cluster, if a VM is currently migrating. If not, first of all, we try to find all VMs that are violating strong VM to host affinity, meaning VM to host or VM cannot reside with a host, but strong affinity. In case we didn't find any type of this affinity broken, we move on to find the soft affinity VM to host affinity that are broken or violated for that matter. And if we don't find any of these affinity groups violated, we go on and try to find VM to VM violation affinity groups. Again, VM to VM affinity violations here are only strong affinities, strong negative or strong positive. In case we found a VM that is violating strong VM to host affinity, either it's strong or soft VM to host affinity, we sort these VMs according to the number of violations, as we demonstrated earlier on. After sorting them, we take the VM with the most violation and try to migrate it by the order. And again, if we didn't find any VM to host affinity groups violation, we try to migrate VM that is violating VM to VM affinity. After we've done that, we sleep until the next interval and start the whole process again. The affinity rule enforcer might conflict with load balancing for that matter. Think of an example that we have a load balancer, let's say that tries to balance according to power saving policy and tries to migrate a VM to a host according to the load balance, the power saving policies we have. And in the background, we have the affinity rule enforcer that is trying to solely migrate a VM by VM to host or VM to VM affinity. But we're talking about, let's concentrate about VM to host affinity. In case we want to make sure that affinity rule enforcement migration is much stronger because it uses the same structure of the scheduler, we need to make sure that our weight model of the VM to host affinity, so it has a larger factor than the other weights and factors here. So in this example, the default value for VM to host affinity groups is 10. That usually will overcome the other factors, and the affinity rule enforcer will have more weight with VM to host affinity groups. So if we have already a VM that resides on a host it should be on, it won't migrate to another host due to load balancing in the background. So again, the decision of a target host will be considered according to the weight factors in load balancing migration and in affinity rule enforcement migration. Now, because we needed to enable this type of migration or non-migration for that matter, if I don't want the VM to migrate off a host, Now load balancing allows the VM to stay on its current host. Or in other words, the target host can be the source host. That's why migration policy unit was removed from the policy units in scheduling, and logic was moved inside the engine. So we talked about affinity groups and creation of some of them that might create conflicts. So in aspects for VM to host affinity conflicts, let's concentrate on two types of conflicts. We have hard conflicts that the system won't allow. The best example for it is one affinity group on the left. A VM A has a strong positive affinity with a host A, and another affinity group, a VM A, that has a negative strong affinity with a host A. For that matter, let's assume that the left group, VM A with strong positive affinity to host A, existed in the system. If we'll try to create the second affinity group that defies the other group, the system won't allow it. But then again, we can have other affinity groups that the system will allow. And in our job is to at least warn the user about these type of conflicts. This type of conflicts will come out of the affinity rule enforcer in log messages form and also in REST API. So let's just go through the possible conflicts that we might have. Again, these are not all the conflicts, but these are classic cases. In short, a VM A has a soft positive affinity with host B, and a VM A has strong negative affinity with host A. Now, because this is a soft affinity, the system will allow it. But again, as the previous use case, this is not a situation that might be desired. One correction, the host on the right should be host B and not host A, but the same use case as before. Another use case is that we have a strong positive affinity for a VM A with host A in one affinity group, and another VM B with the same host A and negative strong affinity, and the third affinity group containing only VM A and VM B with strong positive connection. Now you can see why this situation is a bit confusing or conflicting, because both VMs want to run together, but VM B cannot run on host A and VM A can run on host A. So the left and right side are a bit conflicting if we join these two VMs together, meaning that if host VM is already on A and VM B wants to migrate to it, it can, because it can't reside on host A. Another confliction is the opposite, as you can see here, with positive affinities on the left and the right, but negative affinity between VMs. Another example is for intersecting hosts. This might not be a clear conflict, but let's say we have a VM A that we want it to run with host A and B with strong positive affinity, and VM A that wants to run in strong positive affinity with host A and host C. Now we can clearly see that host B and host C are not non-intersecting hosts. We can say that the clear host that needs to be run on is host A in both groups, but host C is not contained on the left side, and host B is not contained on the right side. We have no intersection here, so it's a bit unclear on where the VM should run. Let's say in case host A is not up. So this is also a possible conflict. Okay, again, so REST API and SDK. So creation and modification of VM to VM affinity groups are available via our user interface and REST API and SDK. As far as for VM to host affinity, we can do it currently only via the REST API and SDKs. Some example for REST API calls, just a simple example. If we want to get all affinity groups, we call it by the cluster ID and the affinity groups. To get a specific group, the same manner with the affinity group ID. If we want to create a new affinity group, we use post call. with the cluster ID and affinity groups. I will show the body of post in the next slide. Same thing goes to put. Put simply edits the affinity group. And let's just move on to the next slide and see how the body of the call looks like in XML format. So an affinity group has a name. It's the list of its VMs, list of its hosts. Again, we can have affinity between the VMs in the list and affinity between the VMs in the list and the hosts in the list. We have host rule and VM rule, meaning for host rule is VM to host affinity, if it's enabled or not, if it's enforcing or not, meaning true for strong affinity or false for soft affinity, and positive if it's true, false otherwise it's negative. Same thing goes to VM. Now, an important thing to notice is the enabled tag. Enabled tag, if true, means that this affinity group, the list of VMs have affinity with one another in that group. If it's false, the affinity between VMs is not relevant. It's not occurring in this affinity group. But there is an affinity between the list of VMs and the list of hosts here. You can notice also positive and enforcing tags here. These tags existed earlier on when the affinity group had only VMs affinity, and mainly for backward compatibility reasons, to mention if VM to VM affinity is positive or negative, and if it's enforcing or not enforcing. Again, we also have the cluster ID here. If we want to post or create an affinity group, this would be the way. Also, for editing, we can use the same body and change the values here. If it's VMs list or hosts or the Boolean values here. Well, affinity groups, VM to VM affinity groups, all types existed in oVirt since 3.5. And VM to host is our new feature. All types exist since the latest version 4.1. We said we can configure VMs to VMs via the user's interface and SDKs. VM to host only via the API and SDKs. So to wrap things up, we talked about that Affinity allows you to define complex relationships rules between VMs and between VMs and hosts. Our new feature addition is VM to host. Again, you can define a VM to host relationship affinity by affinity labels. And we talked about that affinity is enforced dynamically and takes the current cluster situation into account. We have the affinity rule enforcement in the background that picks violations of VMs and migrate the VM. This migration goes through the scheduling process, meaning through filters and scoring units, and picks the target host for migration. And then basically that's it. So I added in the link here of the video these related topics. As you can see, you can read about VM to VM affinity, affinity labels, the scheduler, rule enforcer itself, and our feature page at top for soft host VM to VM affinity. Now, let's see if we can answer some questions in our live chat. Again, I remind you that if you have any questions or comments, you can post a comment in the video itself, or use the oVirt users mailing list, or send me a personal email. So for the next minutes, let's see if we have any questions on chat. So I'm waiting for any questions here on the chat. Again, if you decide to ask a question later, it's perfectly fine. We can see it in the video here. Again, in the mailing over list, I will wait another minute or two for your questions. By the way, for those who don't have a YouTube channel, you might need one to be able to participate in that chat. For everyone that is new with the YouTube Live event. I can see a question about warnings about VM to VM Affinity. Currently, we can see a VM to VM conflict warning in UI. We do have it. As far as for VM to host, once it gets also to UI, then we'll have it as well. Look at the release, yeah, 4.1, now in beta. Thank you, Mariana. Okay, guys, so the chat is not closed yet. And you can keep asking questions here in the channel. Let's see. Yes, the cost calculation algorithm is a part of the schedule model. As I mentioned earlier on, regarding counting the number of violations. These are a part of the soft affinity, meaning the VM to host affinity weights. So we count the number of violation, and that is the score of VM to host affinity. Thank you, Martin, for the elaborate answer. Okay, guys, so the chat is still open. If you have any more questions later on, you can also contact me or contact us in usersovert.org in the well lists for any further questions. Thank you.